Welcome back to Tech Talk with Katie, and thank you so much for such an overwhelming response on the previous episodes. We are going to be doing a 3-episode series this time on 3 diverse topics with our esteemed guest. The esteemed guest that we have has 27 plus years of experience in the IT industry, where he donned the hat of a service engineer fixing those big room-sized servers, to now where he's serving in the leadership position at IBM. He is also the quantum ambassador for IBM. I am talking about none other than the famous Rohit Sood. Let's catch up with him on the other side of this conversation. But you know the drill. Don't forget to subscribe my YouTube channel and do press the bell icon. Let's catch you on the other side with Rohit Sood on quantum computing. Welcome to Tech Talk with Katie, Rohit. It's an absolute honor and a privilege to have you with us today.
Pleasure is all mine, Katie. Thank you so much.
So at Tech Talk with Katie, you already know that we simplify complex technologies so that even a layman can understand. So the topic today is quantum. Who better person can we have than you, who's the ambassador of quantum for IBM? So the first question I wanted to ask for the audience out here is, what exactly is quantum computing?
Wow. So you said simple and then you added quantum on top of it. Let me try. So when you look at quantum is a field of science which has computer science, mathematics, and physics and principles of quantum mechanics, bringing in together to solve complex problems which a classical computer will take ages to solve in this planet Earth, right? Does it sound simple or complex? So when you look at quantum today, when you look at versus a classical computer works on 2 bits, everybody is aware of. It is either 0 or 1. But when you look at a quantum computer today, it actually works on a fundamental of quantum physics, which says if 0 and 1 can coexist together at the same time, that's the principle which helps give a lot of performance to quantum computing and which helps solve this problem much faster as compared to a classical problem, right? I'll just give you an example to make it more simple. If you flip a coin, whether it will come heads and tails, you will actually come to know whether if it's heads and tails, if it lands at rest. But till the time it is in the air, it is flipping, can be 0 or heads or tails at the same point of time. That's what the principle of quantum computing is, and that's what makes it different from classical. Whereas classical works on zeros and ones, quantum on the similar side have zeros and ones, but they can coexist together at the same point of time.
Okay, so why will anybody want to use quantum? Why is it even required?
That's a good question, Katie. So when you look at problems today in terms of your financial algorithms, or when you look at chemical industries, and when you look at health industry today, right? The classical computing today is solving those problems, but there are few problems which takes a lot of time and to solve those complex algorithms. For example, to give you an example fundamental of make it break down into simple thing is integerization, factorization of an integer, right? If it's a small integer, a classical computer can do it very efficiently, right? But if I come and give you, can you help me run a program which can do factorization of a 1 billion, some lakh, some 1 million, that would take classical computer a long time, right? And quantum computer can do that factorization in a matter of seconds because of the fundamentals which I talked about, having zeros and ones at the same time, right? So there are problems in this universe which will need classical to help solve them, but then there are few things which cannot be solved by classical in that human time frame, which quantum adding to that piece of technology will help solve it much better. So we talked about classical versus quantum, Katie. Everybody loves coffee, right? So a caffeine molecule which goes inside a coffee, how much molecules are combined together to deliver that taste. Now if you want to change that taste, today a classical computer, if it needs to analyze a caffeine molecule, it needs about 2 to the power of 48 bits, right, to analyze the full caffeine molecule, which has carbon, hydrogen, oxygen combined together into some different forms and shapes, right? Now, to give you a view of how quantum would do that, right, 2 to the power of 48 bits, which is 2 to the power of 48 of zeros or ones together, and that's how complex it is, right? Now, we did the similar analysis of a caffeine molecule with just 160 qubits on a quantum, right? And to give you a view where we are from a scalability of a quantum today, IBM announced the processor of the latest processor on quantum, which actually is a 434-bit quantum processor, right? So we can actually do multiple caffeine molecules together and give it in a few fraction of seconds output as a result.
That's amazing.
So that's the power of quantum, which will help solve those problems, which classical is going to take long time to solve.
So clearly it means quantum computing is leaps and bounds ahead of what classical computing does, and
for small portion of the problem factor, right? Not all.
So it does not replace classic computing is what you're saying?
Definitely not.
Interesting. I have a few questions on that front. So before we get on to that, what kind of infrastructure does a quantum computing require?
Okay, so let me give you answer to that by telling you what the problem is when you run a quantum computer, right? So when you run a quantum computer, you are actually making the atoms talk to each other. When you say atoms, these atoms are prone to noise, prone to errors. Now we need an environment which can help them reduce that error, right? Now to do so, to give two atoms to intermingle with each other, you need an environment which is 1,000 times lower than the outer space temperature. Now how do you get that into these environments?
1,000 times lower than the outer space temperature.
Yes. So wow. These are actually quantum computers are nothing but have refrigerators inside them, deep refrigerators which actually help keep the quantum chips at the temperature where these quantum atoms or quantum neutrons can mix each other in those low noise, low error areas. So that's how, when you look at today, the capabilities, actually the industry is evolving, the technologies are evolving. We are actually looking at leaps and bounds in terms of what quantum would be able to do if we are able to tackle this energy constraint when it comes to freezing them at this low temperature.
Okay, so clearly it requires a specialized way in which quantum computing is arranged. Do you see it becoming a part of a normal data center, right? So we have a lot of cloud data centers available. We have private data centers also available with the enterprises. So do you see quantum becoming a part of these data centers where a special place is given to quantum computers and they are being hosted? And I have a follow-up question on that, but I'll ask that question first.
I foresee a big data center where, as I said, we'll have classical computers and quantum computers coexisting, considering meeting those challenges which I said to you.
Okay, and do you see so we are in the cloud era today, right? Everything is on cloud. All the servers that we are accessing, storage, everything is on cloud. The classical computing is on cloud. So can we have quantum computing also made available as part of the same cloud, right? So I'm accessing certain classical machines, classical computing machines, and I'm running my workloads over there, but I need, for some of my workloads, I need quantum computing. So I can utilize it the same on the cloud.
I don't see the future. It is available today, KD. So you can actually go and access a quantum computer on an IBM cloud without any charge for you. So if you want to run a small simulation algorithm, I'm saying there's a simulators, and you can actually you can run those quantum circuits on these actual quantum computers free of charge on IBM Quantum Cloud today. So you just have to go open a IBM Cloud account, and you'll be able to run your codes on quantum today.
Awesome. That's amazing. So what do you see as the key use cases for quantum today, right? What's the practical usability that you see happening today?
So when you look at quantum today, we have key problems, as we discussed, right, which cannot be solved by classical computer, or classical takes longer time to solve, will take longer time to solve this problem. So just giving a one example which is related, which everyone could relate to, right? I think batteries. Today, batteries are part and parcel of our lives, right? When you talk about mobile phones, when you talk about EVs, when you talk about cars, two-wheelers, four-wheelers, I think all of them today are going into a major component is a battery over there. Now, how to make batteries efficient? It is all about understanding the new elements, the new capabilities of carbon, lithium, and how do you merge these two together to give you the best carbon lives, right? Now, whether classical computer can do that, answer is yes, but it takes long time to solve that problem, right? Quantum, we are actually working with many large industry automobile manufacturers, where we are helping them, onboard them the quantum journey, and help using quantum, making them to make those batteries efficient. And that's one of the use case which we talked about.
That's interesting. So you're saying that I will be able to use my phone for 7 days without charging?
Yep, hopefully yes, in upcoming future, KD.
That is great, and I can take my car across the length and breadth of India in a single charge.
Hopefully that day will come. Yes.
Oh, that's very nice. That's very environment friendly as well, right? So quantum computing is actually going to contribute a lot in the carbon footprint reduction as well.
100%, KD. So I think energy efficiency, I think everybody is talking about making the planet sustainable. The 14 sustainable goals, and relating to the major is the carbon savings, right? And I think everyone is working towards that, and this will be the leaps and bounds on that capability.
So that was Rohit with his insightful views on quantum computing. We will be back with him in the next episode with power systems. Stay tuned for the next episode on Tech Talk with KD. If you like the content, do like and share the video. Don't forget to subscribe my YouTube channel Tech Talk with KD, and do not forget to press the bell icon. Thank you.